thank you, Fraser, for introduction. So I am holding this talk essentially for Emilia Götz, who is right now on her holiday honeymoon. Yeah, so essentially those are her slides. Okay, so it will be about polymorph screening using XtaLAB Synergy-ED.
Not working.
Yeah, okay. Yeah, so XtaLAB Synergy-ED. Yeah, despite we are having quite different hardware, the workflow and the way you process and analyze the data sets between electron diffraction and single crystal X-ray diffraction are very similar. There are, of course, some differences, yeah, but essentially, yeah, the measurement itself, from the point that you have the diffraction and then the analysis goes very similar. But to get the full potential out of the system, some kind of automation is needed or could be beneficial. So hardware-wise, I'm pretty sure you have seen this a couple of times now. Synergy-ED is more than the sum of its parts. You have a 200 kV LAB6 filament that is used to generate the electrons. You have optics from GEOL, of course, that allow you to change also the detector distance virtually. You have some optics behind or between sample and detector. HyPix-ED is a detector, single electron counting detector that we also use for X-rays, of course. And everything is driven by XtaLAB Pro. Yeah, sample stage allows you to center the crystal in 3 directions, and you have a single tilt axis. The great thing here is that because it's based on a GEOL system, you can have all kinds of different sample holders and sample environments, like cryotransfer. You can cool, you can heat. You can have things for inner transfer. You can have gas cells. Yeah, this is it. Good. When you start your measurement, or when you bring in your sample into the vacuum, you will typically see a wide range of different crystallites. And these range of crystallites, they have, of course, different quality. You don't know right away, will this crystal be nicely diffracting or this one with a nice edge shape. Sometimes you have to test many different ones. If you already have so many crystals on your grid, you may also have different types of polymorphs. So especially when you are in the let's say in the pharmaceuticals or something, there will be a lot of different polymorphs that you can screen. Also, you would see probably if there are any impurities in your powder. From a single grid, you would typically measure like your 10, 15 different grains before you have enough, or you are sure that you have enough data for the publication. And in the end, you need some way to manage your data sets. So we have this result viewer for micro-ED that lists up all the experiments. You can filter them for the user, for the type of material. For temperature, you can put comments. For each line, you get diffraction image, visual image, an overview, basic information about the crystal system, analysis results, and the AutoChem, of course. Yeah, this interface allows you to sort the different data sets. Also, you can choose data sets that you want to merge afterwards from here. Yeah, as we are looking at different crystals, we can also do a couple of different things. So, for instance, in XtaLAB you can queue measurements. Yes. So one of the things that you can do is called crystal screening. Essentially, you are deciding for a couple of different crystals, and you are just making like maybe a 1-degree scan or something to see is it crystalline at all, yes or not. Another thing that you can do is crystal mapping. Crystal mapping means that you measure a bit wider wedge of reciprocal space that allows you to determine the unit cells. And in the ED viewer here, you see we measured just our calibration crystal inlet, P2 or in P2 there's 2 different polymorphs. And you can directly see this either from space group or from the unit cell parameters what you have in each data set. Yeah, once you know, let's say, okay, this crystal diffracts, you can start a full measurement, or maybe from your screening result, if you're looking for a specific polymorph, then you can revisit this grain. The position on the grid is stored, and you can make a full measurement on these grains. The next is a short video that should show you how this works. No? Ah, okay. Yeah, all right. So we have demonstrated to you yesterday in the lecture the automatic, let's say the manual centering of crystals and the manual workflow. But here we have in a short video the workflow you would employ for queuing of crystals. It all starts with finding a suitable crystal, check for diffraction quality, and then essentially the centering can be done by XtaLAB Pro. So you just are going onto the middle of your crystal, and then we will set up a queue of different measurements. So my colleague Emilia just put in like a new data collection. Elements common can be, for instance, the temperature that you measure at. And if you want to obtain just a unit cell, then a short scan range like plus minus 20 degrees is sufficient. You can tell XtaLAB what you want to have, unit cell only or full data analysis with structure solution. And you essentially add in more data sets. This is now speed up 16-fold, sorry. Yeah. Essentially, the software will then center the crystal, start the measurement, and you are getting the unit cell information that you want. After you did your range of measurements, you can analyze it. For instance, for this presentation, like 34 grains were measured, and we found different polymorphs in our ELIT crystal mixture. So we just mixed the powders together, grind it, and put them on the same grid. And now the question is, how can we efficiently analyze these materials? So there are clustering tools. They were introduced already by Robert yesterday. Essentially, this is a dendrogram here, and you are looking here at the more similar unit cell parameters are, the smaller is the distance here in the vertical axis. And you can see that two different polymorphs can be found. One in the, this is the centrosymmetric one, and the other one is the one in orthorhombic. You can also visualize the data. For instance, you look at different redundancy in the data sets. You can look for completeness, for instance. Even if you have a low complete data set, you could still, they still have very good quality and can be used for merging later on. Yeah, exactly. So data sets from screening can be merged, and technically you don't need to remeasure them, but of course you can, of course. Why do you merge data sets? Yeah, essentially to get higher completeness. You will get also nicer ADPs. You improve the signal-to-noise ratio, and effects from dynamical scattering are, let's say, leveled out a bit. If you have radiation-sensitive crystals and you measure only smaller batches from them, then you have essentially you created a data set that includes less radiation-affected frames into this. And in our clustering tool, once you have decided which ones you want to have, in here there is an option to get you the merging script for XtaLAB. Just for a comparison, single data set here on the left, the connectivity is there, it's great, but the ADPs are a bit strange. If you merge a second data set to it already, then everything looks kind of fine. Monoclinic and orthorhombic polymorph, yeah, this is just an illustration so you see what is the packing of it. And yeah, then we can have a look a little bit on publications that we had. You know that most of the things we measure in the application lab in the course of instrument demonstrations, they very often go directly into publication, and by now we have a lot. And yeah, and our customers, of course, they publish now also a lot of things. Mostly still we measure at office, I would say, MOF crystals, COF crystals, and small organic molecules. But of course, sometimes you also have the radiation hard inorganics as well. So there's basically no limitations, other than maybe the material is incompatible with, let's say, vacuum or they are radiation sensitive, and then we have ways to work around those. So, for instance, you can do cryotransfer. We showed it yesterday to you. This is a Gata and ELSA cryotransfer holder. You place your sample here in the top. You have a shutter mechanism that prevents it from icing. This particular sample just loses crystallinity when it's exposed to vacuum at room temperature and maintains nice crystallinity at 100 kelvins. Yeah, so cryotransfer stabilizes it in vacuum, reduces beam damage. Yeah, you get higher resolution as in X-ray diffraction and so on. Yeah, then we have another nice study. So this particular crystal was once measured in vacuum and once was cryotransfer. In cryotransfer, you can localize co-crystallize water in the room temperature case. You are not seeing this, and you have a different material in the end. Another such study was done. We had an internship student, Oskar Kaszubowski from University of Wrocław. So he has this antiviral drug, tenofovir, and this material has a lot of different phases and solvates and hydrates and things. Essentially, when you are dehydrating the hydrated forms, they form very fine powders, and up till very recently, there was no single crystal structure available, and we could just measure this. Yeah, just dehydration in vacuum is a thing. That's good. This copper morph here was synthesized by our colleague Maciej Krzywa from the powder diffraction group. He synthesized this material at his when he did his PhD in Konstanz. This material we sometimes demonstrate here either for powder diffraction or even for single crystal X-ray diffraction, because sometimes you find crystallites that are large enough for X-ray diffraction. Great. When we were testing different type of in situ holders, we did also temperature studies, and essentially this material has a reversible phase transition from a low temperature alpha phase in tetragonal to a cubic phase when you heat it up. And what you observe here is essentially a distortion. You see here the copper-copper distances. They are then equal in the high temperature phase. Another interesting sample that we had is this here. Currently, Claudia Weidenthaler and co-workers, they are preparing a manuscript. They are in the Max Planck Institute, the Kohleforschung. So essentially, they do a synthesis in the melt. They have a precursor of an iron oxide and some ammonium phosphate salt, and they do various steps in the synthesis. And what they get out is a great mixture of different materials. As you can see from the SEM pictures, there's large crystallites, there's small crystallites, and everything in between. Some crystals are large enough for X-ray diffraction studies. This is quite a small crystal with 13 microns in the smallest direction, 1 hour on Synergy-ED. So then there are two other materials that pop out here. They are then much smaller. I don't even know if you can see that here. They could be analyzed by 3D electron diffraction. Yeah, so once you identified all of your samples and you match it up with the powder diffractogram, then you can see if you found everything in your mixture or not. Just to give an idea how much the automation helps you, when we received this material beginning of last year, maybe we measure 12 grains and spent quite some time on Synergy-ED to get a decent result out of it. But with the new automation features, we can speed up things quite dramatically. So instead of only measuring 12 grains, we get 50 now. We can analyze the data set by this nice viewer tool, and maybe we only spend a total time of 1 hour on the system after we identified which might be suitable grains for the full measurement. Yeah, and then I already come to my conclusion. 3D electron diffraction allows you to solve structures from very small crystallites in only a few minutes, of course. Yeah, you can have different in situ holders. Cryogenic workflows help to stabilize solvates and hydrates. Automation features will allow you to enhance the capabilities of the system, especially in this case for polymorph screening. Yeah, and 3D-ED is applicable for almost any kind of structure as long crystallinity and sample size are given. On the webpage, you will also find our list of publications. We are maintaining this. Kai, please correct me if I'm wrong. This is publications involving measurements here or everything on Synergy-ED? Everything on Synergy. Everything on Synergy-ED measured. Right now, 43. Yeah, very good. So then, thank you very much. I'm open for questions if you have any.